Wow, wow. Welcome back, organic cats. Here we are. Here we are. Hopefully, yeah, we will be finishing my material today. This will not take the whole time. So, go ahead and call it early when we finish. Then maybe Wednesday I'll work through a bunch of problems. In the meantime, let's finish up from the aldol from our basic different type of alpha substitution reactions. Off with the Michael reaction and Robinson annulation. Okay, so the Michael reaction is when we see a conjugate additions between alpha and beta unsaturated carbonyls that have very electrophilic sites undergoing both 1,2 addition and 1,4 additions. The 1,4 are a conjugate addition. So it's not just having an alpha hydrogen, it's also having a beta hydrogen further down the line. And essentially we have this type of structure. Hydrogen. So a monosubstituted alkene making it into a carbonyl, CH3. Now, this can undergo this resonance to form, while not very stable, it is a resonance structure of this. But this will help us see the next. So the enol intermediate has to do with the loss of alpha hydrogen, thus stabilizing this structure, forming enolate. But here is where we get this. Well, this is a very important structure because we can then stabilize this structure by separating charges. I hate that. Separating our charges. Stabilizing this resonance structure. Because you're essentially getting the positive much further away from the negative, thus allowing this resonance structure to breathe. Essentially what we're doing is we're getting from 1 to 3, we're swinging that up, swinging that out. Now the 1,2 mechanism has a nucleophile attacking at the carbonyl. So this structure, rather than seeing a loss of alpha hydrogen, we're seeing a nucleophilic attack at the carbonyl. Step 1, form our tertiary, and then we pronate. Thus forming tertiary alcohol. There's our 1,2 mechanism. But alternatively, we can see a 1,4. So that's the 1,2. 4 could have that nucleophile attack here. That swing up there, swing over there. Thus, we form protein. And thus we have H. And here's the thing, is that this can undergo a tautomerization. Right about this, because we have an enol, that enol, not super stable, can have our tautomerization. Tautomerization to form our ketone. So we had the nucleophilic attack, and now we reform ketone having lost alkene. Now, most alkenes won't see a nucleophilic attack like that. But in the presence of these alpha beta unsaturated ketenes, we can see that. So, this case, we can see protonation occurring either on the oxygen or the alpha carbon. Now, this reaction is called the Michael addition, where the unsaturated ketone is a Michael acceptor, and the nucleophile is called a Michael donor. Just like we have an acid base, that the acid is the proton acceptor, and the base is the the acid is the electron acceptor, and the base is the electron donor. We have the same thing with the nucleophile being Michael donor, which is going to be our electron donor, the same, and our Michael acceptor, the ketone is a Michael acceptor. So most of the times, these donors will have a lot of electron withdrawing groups. Help stabilize this. So here's a list of common Michael donors and common Michael acceptors. I'll put the donor over here and the acceptor on this side. So the Scepters, I'll start with them. Our basic, we could have an aldehyde. We could have a unsaturated ketone. We could have unsaturated ester, unsaturated amide, we could do this with a unsaturated nitrile, to form this an amine, and we can form, this one's a little unusual, unsaturated nitro group. The donors, we could have the Gilman reagent being a donor. We could have a this is an unsaturated amine, enamine. We could have our basic diketone. Basic keto ester. basic keto nitrile, we didn't see before, and a base. Oh, I'm gonna have to go up here because I ran out of room. And a basic keto nitro. So you see a lot of repetition. You hear that nitrocyano, all the same groups. The only difference is that this is unsaturated, and these are usually have a nice lone pair to donate. So let's just look at this. Look at some reaction like this. All these lone pair, R minus, charge lone pair, charge lone pair, charge lone pair, charge lone pair. All these with electron withdrawing groups, pulling the electron density away from the lone pair, helps stabilizing. Okay. So look at cyclohexenone. So it'd be like 2-cyclohexenone. Acting with the Gilman reagent of vinyl copper lithium, or vinyl copper. So the first step, we attack in the 1,4 position, and then we protonate. Step 1, adds. Step 2, protonate. And of course, it's going to go some rearrangement. So, rearrange. So this is suddenly now center carbon. So this is no longer conjugated. So with our lithium dialkyl cuprates, we can add the enolate to acyl halides. So it's possible instead from this spot to do something interesting. So from that same intermediate, if instead of adding acid, add alkyl bromide, this is going to act as an SN2 attack. Rearrange, put the negative charge on that alpha hydrogen, and so we can form instead still reform the ketone, but now 1, 2, 3, 4. 1, 2, 3, 4. So we can now attack and form that. It can do similar to the acetoacetic ester synthesis or the malonic ester synthesis as a synthesis to a Michael addition. So remember with that, it was possible to, once we form that carbanion, we could then do an SN2 attack on a alkyl halide to then add to the alkyl halide, taking off the halide. So just some reactions that we can expect to see. Robinson annulation. Now, Robinson annulation is actually a modification of the Michael addition. If the Michael addition undergoes a strongly acidic or basic conditions, it will spontaneously cyclize to form a six-membered ring called the Robinson annulation. So essentially, looking at this, we have a ketone with an alpha hydrogen, and we're adding to a alpha beta unsaturated ketone under basic conditions, which step one is to depronate this guy. Depronate that guy. Remove that, and that's going to form the negative charge, which is going to attack at the 1,4 position. So we're going to form this intermediate. Water will push it back. So 1, 2. So see, am I drawing? 1, minus. Now, in the presence of water, we're going to essentially rearrange, reform our base. So this is going to swing down, this is going to swing up, and depronate. We're going to reform, draw down here. Three. All right. So we've essentially pronated that spot. Reformed our OH minus. Well, from there, let's see if I can delete it. See if I can move this up or not. Be nice if I could. Now I'll just redraw. Not a big deal. Okay. Aha, that's nice. This, yeah, we draw it anyways. At least we draw that part. Yeah, there we go. From there, presence of base, we can undergo another alpha hydrogen loss. Attack there. Which, from there, we have an intermediate. One, two. now attack ketone, carbonyl, causing that to swing up. So we've cyclized that as a bicyclic ring. So that's 1, 2, 3, 4, 5, 6. Minus. And in the presence of water, air and pronate. We have a bicyclic C ketone. Now this right there is maybe not the most stable. We'd rather reform the unsaturated ketones. So what we have here is now beta elimination. The presence of base, depronate here, such that our cyclic ring H will then swing down, beta eliminate our OH, and form our final Robinson annulate. Now let's look at a quick example of this. Do the full mechanism right here. Plus, yeah. Presence of a strong base. Oh, let's say oxide. Step one is we form the minus on that center between the dicarbonyls, and that attacks in the 1,4 position. So the first thing, see the 1,4 attack. So two. And then we draw that down here. Might have to keep redrawing this and erasing as we see fit. Forming this as the now as we attack, another equivalent. Now you have two different carbonyl groups. However, one of these is more electronegative than the other. And remember that oxygen of that ester donates electron density into that carbonyl. So that ester is actually going to be further, it is going to be a weaker electrophile than the straight up carbonyl. So as we form the beta, with the alpha carbanion ion, we're going to attack the carbonyl, the ketone, rather than the ester group. So I'm counting 1, 2, 3, 4, 5. Let's see. 1, 2. Oh, I lost a carbon. 2, 1, 2, 3. Yeah, I lost a carbon. Shit. Okay, let's erase. Okay, let's read all that because that is bad. 1, 2. 1, 2, 3. 1. I'd say, why didn't you yell at me? But I mean, obviously, you're not going to yell at me if you're not here in the meeting. So that means that's going to be, yep. 1, 2, 3. Now that's better. Now that's better. So with that in mind, I count 1, 2, 3, 4, 5, 6. 6 carbon chains, so we'll form a bicyclic 6 carbon compound. So cyclohexene. Just checking. Yep. Okay. 1. Then in the presence of water or methanol, protonates, and so let's go ahead and form what before the beta hydride elimination. Even though it's not going to last long. Finally, you form the final product. In my particular book, it's the ethyl group. So if that doesn't really matter, it's essentially the esters hanging along. Okay, let's look at one more real quick. Okay, sorry. I want to look at 2 more versions of the Robinson annulation. One, the hypothetical reaction we were supposed to have done in lab, and the one we actually did in lab real quick. So both of them are with ethyl acetoacetate. So ethyl aceto acetate. So there's the aceto. This is your aceto. There's the ethyl. And there's your acetate. Ethyl acetoacetate, as that would be our Michael donor. And we were supposed to use our trans-chalcone, which was from our aldol condensation. It's supposed to be piperanaldehyde. So as this is undergoing, let's go remember what first thing would be formate and in strongly basic conditions. First thing we're doing is we're deprotonating the dicarbonyl, which is then attacking at the 4 position. So I'm going to just call that phenyl group and phenyl group just to make this a little bit easier. So we're attacking the 1,4 position. I'm going to just put those 2 steps together just to make things a little bit easier. So I'm going to draw sideways because God knows this is a big chunky molecule. Two, three, 1, 2. Phenyl. Okay, now on the other reactions we've done for this, we would have deprotonated the next step. We would have deprotonated alpha hydrogen on the Michael scepter. But you'll notice here, if I deprotonated the proton, the only alpha hydrogen on the Michael scepter, we're kind of SOL because we won't be able to form a very good ring. You would be able to form a 4-membered ring, and hopefully we remember 4-membered rings are not particularly stable. Thankfully, here's our alpha hydrogens that we can deprotonate. Deprotonate there and still form a 1, 2, 3, 4, 5, 6-membered ring. So I'm going to do that. It just so happens that it's not necessarily where we would have thought they were going to be. So minus phenyl. And then, of course, last step, we'll just say, we'll combine those together. Last step, of course, deprotonating. So to form this ugly compound. So that's essentially what we would have formed. That's what we were trying to form on the Robinson annulation lab. At least that's what should have been formed if, and here's the big thing, if and only if that was our starting reagents. Fortunately, I could not get enough trans-chalcone to form, so instead we did the same thing with cinnamaldehyde, which has a very similar structure. So instead of, we'll still use the ethyl acetoacetate. Now our group is it also does not have any alpha hydrogens on this. So combine this together. The big difference is only that if I draw the final structure, well, that's the same. The only key difference here is what the functionalization on this benzene ring, this metal ring, and that we've lost, that this is now a hydrogen here. That's the only real difference. Other than that, it should be more or less the same overall product. And when we look at that product, what will you see? You'll see CH stretches from the benzene. You'll see C double bond C stretches from the benzene. Maybe see a C double bond C from the alkene. So you should see some carbonyl stretches, both, maybe several. One shifted a little bit differently because of the ester, and a C single bond O stretch. And of course, some sp3 hybridized CH stretch and some sp2 hybridized CH stretches. So that is just examples of, these are really complicated reactions. Yes, they are. But they serve a purpose of how some natural products are being formed. Essentially, how you can form very complicated materials from relatively simple products. How you form a lot of these bicyclic rings. You've got to remember, think about steroids. Steroids are a series of bicyclic rings. And like, how do you combine ring to ring to ring? Well, if you can get these guys to cyclize and dehydrate, you can form these conjugated rings, which is a lot of what steroids are. Okay, that is where we're going to end today, way super early, but well, 10, 15 minutes early. That's all of my material. That's all fair game that we covered. So we'll look at that and look at some homework problems next class period.